Hi everybody, welcome back to Anth 160 World Archaeology. Today we'll get into our second lecture in Module 1 entitled, Will the Real Hominin Please Stand Up? As we learned about in Module 1.1, Charles Darwin played a pivotal role in shaping archaeological theories about the antiquity of humanity. In this module, we'll explore in more depth his idea of branching evolution. In The Origins of Species, Darwin proposed the idea that species lineages change over time through natural selection and are derived from a common ancestral lineage. Darwin basically argued that humans, apes, monkeys, prosimians all share a common original primate ancestor. Sometime around 52 million years ago, prosimians break away from these other primate groups, and our direct primate ancestors, go on a totally different set of evolutionary journeys from these early prosimian ancestors. As a result, our ancestors share more DNA in common with chimpanzees than with any other primate. The real impact of Darwin's theory of branching evolution was that modern humans are descended from animals, not a primordial ancestral Adam and Eve human ancestor in the way that many biblical theories of human evolution propose. For Darwin, the transition from ape to human was defined by four basic characteristics: a big brain, bipedal locomotion, tool making, and small canine teeth. One of the major questions of the 19th century has been which of these four characteristics occurred first. Up until about the mid-20th century, archaeologists largely believed that it was the big brain that developed first and distinguished our hominin ancestors from other apes. This first development of the brain then led to other things like bipedalism and toolmaking. But scholars have now taken a different approach, arguing for what's called mosaic evolution. Basically, mosaic evolution means that different characteristics develop at different tempos, and each of those traits influence the development of others to a greater or lesser degree. Basically, mosaic evolution means that you can't have the development of the big brain without walking on 2 feet, without tool making, and without similar developments in cranial anatomy with smaller canines. So today, we're going to focus in particularly, though, on this idea of bipedal locomotion and talk a little bit about what it is, where and why, when, and why we developed this ability to walk on 2 feet. So there's several kind of core anatomical features that characterize our ability as humans to walk on 2 feet. And I'll talk briefly about 6 of these major ones today. So the first big one is the placement of the foramen magnum, which is that large hole on the back of your cranium through which the spinal column passes. In quadrupeds, the spinal column runs parallel to the ground so that the foramen magnum is actually placed more towards the back of the skull. In bipeds, however, the spinal column runs perpendicular to the chin and the ground to keep us upright. As a result, the foramen magnum is located more towards the bottom of the cranium rather than towards the back. Another key difference between quadrupeds and bipeds is the S shape of the spine. In quadrupedal primates, the center of gravity is located near the center of the torso. This is different than modern humans, humans whose center of gravity is actually in our pelvises. That lumbar curvature of the spine helps to bring the center of gravity in bipeds closer to the body's midline, so it helps keep us balanced. Humans have actually one more lumbar vertebrae than apes do, and these vertebrae are also larger than our ape cousins. The larger size and number of vertebrae in modern humans creates a more flexible lower back that allows the back to kind of swivel forward when walking, again, helping us maintain our balance. One of the other kind of core features that we see that's different between apes and humans is the length and width of our pelvises. So in anatomically modern humans, we see that the pelvis is shortened and broadened, which helps balance and creates a wider birthing canal for women. In humans who have wide hips, the femur is angled so that the knee is actually closer to the body's midline than the hips. This helps to bring the knees closer together, placing the feet directly below that center of gravity. In quadrupeds, the center of gravity is actually less important during walking because they're supported by 2 more extra legs. So you can see that a lot of these kind of anatomical shifts that we see in modern humans is linked to maintaining a good center of gravity. We also see a difference in the length of arms and legs in response to living outside of trees. So modern humans have shorter arms and longer legs compared to our primate ancestors. As a result of this development in our arm to leg ratio, humans have a larger heel bone compared to chimps. This large heel helped provide stability and absorb high force during heel strikes. Humans also develop what's called a non-opposable big toe, which lies parallel to the other toes and limits lateral movement. Human toes are generally shorter than other primates, which also limits our grasping ability with our feet. Most of human development associated with these kind of critical transformations, like walking on all fours to walking on 2 feet, occurred in Africa, primarily between Ethiopia and Namibia. The oldest African ape that we have to date in the archaeological record is 23 million years old. In addition to finding kind of archaeological evidence for human origins in Africa, there's also some genetic indicators for this origin. Specifically, mitochondrial DNA, that's the DNA that you get from your mom, has provided evidence that indicates that there was a critical divergence in humans and chimps roughly 6 to 8 million years ago. We also see lots of fossil evidence for these early hominin ancestors. So there's several instances of early fossil evidence for bipedalism found in Ethiopia, particularly in the Hadar area. So this early fossil evidence was first reported by Tim White in 1994, and what he called was the Aramis site. So what White found was 17 individual bodies, basically dating to about 4.5 million years ago. What White was able to determine from these remains was that these individuals were bipeds, but had slightly different ways of getting around than anatomically modern humans. One of the biggest discoveries in this region of Africa was the Hadar site in Ethiopia, where fossil remains were discovered of the first true biped in Africa, attributed to our ancient ancestors Australopithecus afarensis. So the remains that were first found at the Hadar site in Ethiopia were fondly called Lucy. So Lucy is about a 4-foot tall skeleton who had a kind of combination of anatomically modern and ancestral hominin features. So Lucy had a small kind of ape-like brain as opposed to the large brain that we see in modern humans. She was definitely bipedal. She was definitely walking on 2 feet, but her arms were still quite a bit longer than modern humans. And she had human-like hands, but her fingers were still very curved in a similar way that we see in our primate ancestors with those curved fingers best for grasping. Another line of archaeological evidence from this region of Africa comes from Tanzania. So particularly the Latoli tar pits. So these early discoveries in the Latoli tar pits were identified by Mary Leakey in 1976. And what Leakey found was 13 hominin skeletons and extinct mammals, all who had been preserved perfectly in this giant layer of ash that had come down as a result of a volcanic eruption. Leakey also documented a 75-foot-long trail of footprints. The footprints that Leakey found had well-defined arches and a distinctive heel-toe print made by upright walking individuals, likely about 4 feet tall, about the same size as Lucy. Leakey estimated that these footprints dated to about 3.6 million years ago. So the question is, why did our hominin ancestors make this transition from 4 legs to 2 legs? Why go through all this anatomical drama just to be able to walk on 2 feet? Part of the answer can be found in the environmental changes occurring between 5 million and 2 million years ago. This is a transition in climate from the period that's called the Miocene to what's called the Pliocene. So during the Middle Miocene epoch, think about 25 to 14 million years ago, Africa was filled with vast expanses of forest and moist woodlands, absolutely perfect for living in trees. Over the course of the Miocene period, there's a general decline in temperature as well as in humidity, and as a result, forests begin to shrink and grasslands actually expand. In the early Pliocene, things become really dry and cool, and these savannas become less forested and more expansive. So basically, between the Miocene and the Pliocene, we see a dramatic shift in the forest coverage of much of the African savanna area where our early hominin ancestors were living. And this precipitated a need to change the way that our ancestors were moving around and living in this area. So one hypothesis for how we became bipedal is that as resources became more widely distributed into these different forest patches during the Pliocene period, it would have actually been advantageous for primates to be able to move more quickly over these greater distances. So while resources were getting more patchy, fossil evidence of early primates indicates that they primarily still inhabited forests, not grasslands, and therefore they would have encountered they wouldn't have encountered the resource stress, which would have really precipitated the transition to bipedalism. So even though we see this kind of changing climate and more patchy resources, most of what we know archaeologically about our primate ancestors says that they still pretty much stuck to these forested areas. And therefore, probably this changing environment and resource distribution wasn't the main driver for why bipedalism was important. A second hypothesis for why we made this transition is offered by scholar Owen Lovejoy. So Lovejoy argued that hominins have a small number of offspring, primarily due to the length of the gestation period. 9 months is pretty long time in the grand scheme of primate and other animal gestation periods. So because females have a long gestation period, they tend to have a smaller number of offspring than other types of mammals. And they tend to have a real investment in the success of that small number of offspring. And therefore, they invest heavily in them. Lovejoy went on to argue that female primates would have actually selected for male mates who could help them provide the love, care, and food that these very precious offspring would need. So, the causal mechanism of evolution, according to Lovejoy, was the fact that men needed to be able to actually provide more food more efficiently for their young, that they were incentivized to do so because of selection, natural selection by female mates, and that freeing up your hands for walking actually allowed you to forage more efficiently, as well as being able to protect your mates and offspring. One final hypothesis to consider is this idea that was originally offered by our old friend Darwin in 1871. So Darwin basically argued that human intellect prompted the use of tools, which encouraged bipedalism. So according to Darwin, we have bipedalism because we have our hominin ancestors starting to experiment with tools, and that experimentation with tools was linked to the development of larger brains. So bipedalism allowed hominins to carry food or other portable items over long distances. It freed up our forelimbs for tool use. So in the next module, module 1.3, we'll dive a little deeper into this idea that Darwin puts out there, that tool use was an important mechanism for driving human evolution. See you all in module 1.3.